Good afternoon. So, this is our 24th lecture, and in the previous lecture, we have seen homogeneous flow modeling, which is the simplest of all analytical approaches for estimation of pressure drop. And then, secondly, we also have done one numerical problem using the homogeneous flow modeling approach. Okay. Today, we will go through this. Separated flow modeling approach. Once again, if you have to go in more details of the separated flow models, then this can be extended up to 3-4 lectures, but we will try to complete this approach in today's lecture only. The major reason is all these analytical approaches were used somewhere in the mid 1950s or so, when actually computational power were not there, and majority of the things on design of different industrial systems were based on the theoretical approaches. Okay, so at that time people have used this type of very simplified flow modeling approaches, but nowadays we see the applications of these approaches very less, because of course whenever a immediate first hand estimation is needed, then people still use these approaches, but because we have now significant computational facility available, so majorly people go for the detailed analysis of complete set of equations using the computational approach. So that's why the applications of these approaches are very less. So we will briefly discuss this approach, so that if you are getting some problem, you can solve the problem using this type of approaches. Okay. So typically, as the name suggests, and we have seen in our initial lectures, that in case of separated flow modeling, we actually distinguish our system into two different fluids. Okay, so even if you have, say, dispersed flow, or even if you have a well separated flow like annular flow or stratified flow, in that case, for annular flow and stratified flow, this approach is working very well. But even if we are having the dispersed flow, then also actually we treat that entire dispersed phase as a single fluid, and the remaining continuous phase as a second fluid. Okay, so that is the whole idea of separated flow modeling. Now, whenever the separated flow modeling approach has evolved, in the very initial days, what people have done, people have simply used the combined phase equations. Okay, people have mainly used the combined phase equations, but they have just relaxed one condition of homogeneous flow approach, and that condition was same velocity. So this condition was relaxed. Is this point clear? And in the second approach, of course, the detailed approach, here two phases are resolved using separate equations. Is this point clear? So, of course, the true separated flow approach is the second one, where two phases are actually resolved using the separate set of equations. For phase 1, there will be separate set of continuity and momentum and energy equations. For similarly, phase 2, there will be separate set of equations, and then of course at the boundaries, in order to interact between the phases, we will be having some mass interaction terms, some momentum interaction terms, and some energy interaction terms. Okay, so that is the actual two-phase flow approach, separated flow approach. Okay, but doing this exact separated flow approach is actually very, very challenging, because there are so many interaction terms are involved, and the value of these interaction terms depends upon the spatial phase distribution. Okay, because if you have some interface between the two fluids, then what are the interfacial force exchange, what are the interfacial momentum exchange, so all these things are to be accounted for, then only actually you can use this approach completely. So that's why this second strategy is actually more cumbersome. So because of the more cumbersome approach, what people have done, people have actually very initial analysis has people have done using the very first approach. Okay, so in very first approach, the combined phase equations were taken, but only difference was that in case of homogeneous flow approach, there also we were having the combined phase equations, but there we were considering that velocities of the two phases are same, so this condition is actually relaxed, and now it is assumed that the two phases are having different velocities. Okay, and this second approach we will not also consider much, because later on in the subsequent lectures, say after 5 to 6 lectures, we will be switching to the computational techniques for resolving multi-phase flow problems, and whenever we will be discussing the computational approaches, there itself actually we will talk about this approach in more detail. Okay, so that's why for the pure analytical purpose, we will just go with the combined phase equations, just segregated by just relaxed by this velocity condition. Okay, okay, so to start with, very simple thing we can consider one dimensional steady flow with different velocities. Okay, so when we are having the different velocities, then while I will be writing my continuity equation, I have to use separate mass flow rates of the each fluid. So for phase 1, my mass flow rate will be rho 1 v1 a1, and for phase 2, mass flow rate will be rho 2 a2 v2, and ultimately the total mass flow rate will be w1 plus w2, and for a steady flow condition, this has to be equal to constant. Okay, and of course whenever we try to deduce these equations further, majority of the time we represent these in terms of mass flux. So corresponding value of individual mass fluxes G1 and G2 are also given in terms of the volume fraction alpha, and where alpha is nothing but volume fraction of phase 2. Okay, so this is volume fraction of phase 2, and then this is also related to total mass flux G, which can be ultimately written in terms of rho 1 v1 into 1 minus alpha by 1 minus x. Here x is nothing but again the mass fraction of phase 2. Okay, then this also we have seen, this is nothing but our momentum equation. Okay, and one major difference in this momentum equation from the homogeneous momentum equation is that here velocity term is written in terms of x times v2 plus 1 minus x times v1. So this is the only difference. Okay, so in case of homogeneous flow approach, what we were considering that velocities of both the phases are same. So if velocity of both the phases are same, then we were simply replacing this term with v. Is this point clear? But here what we are considering that the mass fraction x has velocity v2 and mass fraction 1 by 1 minus x has velocity v1. So we are actually differentiating here the velocity term. Is this point clear? So that is the only difference. If you see, this equation is nothing but a combined phase equation only. Okay, so in combined phase I have to write down the total velocity. So when I am writing the total velocity, in case of homogeneous approach, I was simply writing here dv by dz in the convective term, because both the phases were having the same velocity. But in case of separated flow model, using the first approach, as I told you that we will be only relaxing the velocity condition, so velocity v1 and v2 I have written individually. Okay, so that is the sole difference in momentum equation, rest everything is same. In the similar way, if you write down the energy equation, in energy equation we were having one term d by dz of v square by 2, where v square was nothing but kinetic energy per unit mass. So when I am writing now kinetic energy, because both the phases are having different velocity, so mass fraction of second phase into its velocity square by 2, mass fraction of first phase into v1 square by 2. So these equations are identical to the homogeneous flow equations, okay, like combined phase equations only, but the only difference is that in place of same homogeneous velocity for both the phases, now we have two different velocities of the individual phases. Okay, so with these equations, if you write dP by dz frictional term. So frictional term is nothing but this term is my dP by dz frictional term. Okay, so if you write dP by dz frictional term, we have seen earlier in case of homogeneous flow model also. So wall shear stress tau W, I can write it in terms of 1 by 2 rho V square into CF. Okay, now question comes that in case of homogeneous flow model, it was very easy to write this because we were considering the same velocities. Now how we can write? So if you see, in that case we have defined one two-phase multiplier. Okay, so two-phase multiplier was phi. Okay, so if I write here phi FO, two-phase multiplier for fluid, so then in that case I will be only using the velocity of the fluid medium over here, because two-phase pressure drop I can write in terms of single phase pressure drop multiplied by the two-phase multiplier square. Is this point clear? So that's why here now by taking the help of two-phase multiplier, even if my velocities are different, I have to write over here only the velocity of the single phase. Is this point clear? And then alpha I have taken function of both pressure and mass quality, and corresponding to that you will be getting this detailed expression for pressure drop. Okay, so this is the detailed expression for pressure drop, and you can see that in this detailed expression of pressure drop, this entire term in the denominator can be written equal to unity if I am talking about what? Incompressible flow. Okay, so is this point clear? So whole analysis of pressure drop is same as that of the homogeneous flow approach. The only difference is individual phase velocities are taken differently, and while we are taking the individual phase velocities different, then when we are doing the replacement for frictional pressure drop, we are taking here help of two-phase multiplier, because two-phase multiplier will help us in writing the frictional pressure drop for a particular fluid as that of the pressure drop of a single fluid. Okay, is this point clear? So now when ultimately the question is, we can simply apply these equations to solve my pressure drop, but I need to determine now two parameters. First parameter is CF and second parameter is two-phase multiplier. Okay, so two-phase multiplier Lockhart, Martinelli, Nelson, Barkozy, these are the people who have done significant amount of experiments, and then based on their experimental data, empirically they have actually obtained the values of two-phase multipliers for different situations, and they have provided some generalized chart. By taking the help of these charts, actually we can determine these values. Okay, so what they have done, they have divided these two-phase multipliers in different ways. Okay, so one multiplier is called as phi FO, one is called as phi GO, third type of multiplier is called as phi F, and fourth is called as phi G. So what is the difference between these four? The difference between these four is, in first case we are assuming that whatever my pipe was there, the entire pipe is filled with only liquid, and this liquid is flowing at the same mass flux as that of the mass flux of the mixture. Okay, when I am writing phi GO, then I am considering again the same pipe is actually filled with gas, and this gas is moving at the same mass flux G. But when I am writing only phi F and phi G, then I am considering that now my pipe is splitted into two portions. Okay, I have one portion of having cross-sectional area A1 and other portion having cross-sectional area A2, and in this first portion mass flux is G1 and in this mass flux is G2, and this combination is so selected that my total area of the complete pipe A, say if A is my total area, that is equal to A1 plus A2 and G is equal to G1 plus G2. Is this point clear? So then what I am considering that when I am using simply phi f as my multiplier, the meaning of that is in the total pipe I have identified that how much area of the pipe is actually occupied by phase 1, okay, and corresponding to that area I have allowed to flow phase 1 separately, and if for that particular portion I calculate pressure drop for this dP by dZ for this phase, if that I multiply with phi f square, then I will be getting two-phase pressure drop. Is this point clear? So that is the difference between the two, because ultimately though what I have done here I have explained you all, but later on when I have given you the plots I have given you only for phi FO, because ultimately we have to do the numerical problems, and for numerical problems we can use any of these multipliers. So only multiplier phi FO I have given in the subsequent charts. However, charts are available for each of these multipliers. Is this point clear? What is the difference between this? Okay. Now, if I consider that my this type of approach is there, which is dividing the area of the pipe into individual areas and then allowing individual fluids to flow. In that case, if my no gas is present in the system, then I will be having 1 by phi f square equal to 1 and phi g square, 1 by phi g square is equal to 0. If I don't have any liquid, then 1 by phi g square will be 1 and 1 by phi f square will be 0. Okay. So it means these are the conditions corresponding to the extreme situations once I have only a single fluid present. So when I have only a single fluid present, corresponding to that my two-phase pressure drop will be equal to the pressure drop of that single fluid, because ultimately I don't have any fluid at the present. So that's why this multiplier is getting actually unity value, and for the other component multiplier value is equal to 0. Okay. And if I have laminar flow condition, under laminar flow condition, so these are the extreme situations. Under laminar flow conditions, we say that 1 by phi f square plus 1 by phi g square has to be equal to unity. Okay, so if you divide your system into individual fluid and individual gas, then whatever the multipliers you will be getting, reciprocal of their square should give us actually unity. Okay, so this mixture rule should satisfy for laminar flow condition, and for turbulent flow condition this should satisfy the power of 1 by 4. And of course, from where this 1 by 4 is coming? This 1 by 4 is coming from the Blasius solution for turbulent flow. Okay, now this is the situation of laminar and turbulent flow. But now when I am considering the two phases separately, like my assumption is in one pipe liquid is flowing and in other pipe gas is flowing. So these pipes are nothing but constituents of the same two-phase flow pipeline. So now in this system I can have 4 different arrangements. How 4 different arrangements? In first pipe I can have either laminar or turbulent flow. In second pipe I can have laminar or turbulent flow. Okay. So one combination can be laminar. One combination can be this laminar, this turbulent. Second combination can be this laminar, this turbulent, and fourth can be both turbulent. Out of these, there are chances of rare occurrence of one combination. Which is that combination which will be rarely occurring? Liquid turbulent and gas laminar. Okay, so if you have liquid as turbulent and gas as laminar, chances of occurrence of this are very less. Because if liquid is turbulent, Of course, liquid will be having viscosity 1 or 2 orders higher in comparison to the viscosity of the gas. Okay, so it means if liquid Reynolds number is high, which is leading to the turbulent flow situation, then there are very rare chances that your gas flow will be laminar. So typically when experiments have been done in the past, of course this type of combination was rarely studied, and whatever the values of these multipliers phi you will be finding, these you will be finding majorly for other different situations like liquid laminar gas turbulent, both turbulent, and liquid gas turbulent and liquid laminar. Okay, so these three combinations you will be majorly finding. Somehow initially I have included one chart to give you the values of all these multipliers, but later on I removed it because in numerical problem we are not using it. Instead of this I am using phi FO only, so that I will show you. So this was the very idealistic approach. Then later on what people have done, they have actually generalized this combination, and it was given as 1 by phi f square power 1 by n plus 1 by phi g square power 1 by n equal to 1. So now this equation is applicable for all laminar and turbulent flows. Now depending upon the flow conditions, for laminar flow n will be equal to 2. For turbulent flow, if turbulent flow is analyzed using the friction factor approach, then value of n will be from 2.375 to 2.5, and if turbulent flow is analyzed using the mixing length scale approach, in that case value of n will be from 2.5 to 3.5. Okay, and this is the variation of phi g and phi f. So along ordinate we have 1 by phi g square, along abscissa it is 1 by phi f square. Okay, and here you can see that for different values of n, the solution of this equation is actually plotted over here. So here you can see the solution of equation 1 by phi f square plus 1 by phi g square equal to 1. For n equal to 1, solution is a straight line, where this point corresponds to all liquid. Here value of 1 by phi f square is equal to 1 and 1 by phi g square is equal to 0, and this point corresponds to complete gas, means alpha equal to 1, and this point is corresponding to alpha equal to 0. Okay, and in between different lines are plotted for different values of n.
सर n equal to 1 के लिए ellipse और
For n equal to 1,
circle और ऐसे
phi g square. Okay, so what you are doing, you are not plotting in the entire system. Okay, this is square here. So in your ordinate and abscissa itself you are including the square. So with square give you a straight line then. Okay, then what we have now, one more important part is there. Say if out of this equation you have to determine the value of wall shear stress. Okay, you cannot determine based on only this single equation, because in this equation there are two unknowns, one is phi f and one is phi g. So what is done actually, one more parameter is defined. This is called as chi-square. This is called as Martinelli parameter. And Martinelli parameter is defined as the ratio of phi g square by phi f square. Now for different values of Martinelli parameter, if you know this value of Martinelli parameter, then, and if you know the value of any one of this, either phi f or phi g, then you can easily calculate the value of the other parameter. Okay, so using these two equations now you can calculate both. So here you can see this dashed line is corresponding to Martinelli parameter of x equal to 1, and corresponding to this x equal to 1 you have value of alpha equal to 0.8. Now can you tell me y corresponding to x equal to 1, when phi g square is equal to phi f square, you are getting value of alpha equal to 0.8. The common tendency is, if my multipliers of gas and fluid are becoming same, our common thinking will be that corresponding to this I will be having almost same distribution of gas and same distribution of liquid. So I should get the value of alpha equal to 0.5. But I am getting value of alpha equal to 0.8.
Mass quality.
This is because here we are considering the volume quality, and gaseous phase will be having low density. Okay, so because of this it will be occupying more area. Okay, so corresponding to that I will be having some asymmetry in pipe size and the amount occupied by gaseous phase. Okay, so because of this we will be finding that value of x equal to 1 is giving me very high value of the volume fraction of the
बस ये
gas.
तो specific gas के लिए
Sorry, yes, this is for gas.
कौन सी मतलब specific मतलब हर एक gas के लिए तो ये
No, so typically if you consider any generic system, in any generic system, if you have one liquid medium, one gaseous medium, so there will be 2 to 3 orders difference between the density of the two fluids, unless or until gas is compressed to very high values. Okay, so for a normal system you will be finding actually always this condition is true. Okay. So this is a detailed curve. Of course, the application of this curve people have seen, and then using the application of this curve, people have obtained that the values of n equal to 1 for laminar flow predicts the data very well, and value of n equal to 1.75 and n equal to 4. These two values actually predicts the data well in between the two different regimes. And of course, if you have to entirely fit the data with a single exponent value of n, then n equal to 3.5 works very well for turbulent flow. Of course, just to avoid the redundancy, I have not given you so many plots over here where this data is compared for different values of n. But this is some common approach that whatever the approach was decided, this approach has worked well. But one important task is when you have to determine the values of these multipliers phi f, phi g, phi fo and phi go using the experimental data, because what I am telling that all these multiplier values are actually obtained based on the experimental data. Okay, then you have to calculate from your experiment the only contribution of the frictional pressure drop. Okay, because whenever we are calculating the multipliers, these multipliers phi are nothing but ratio of dp by dz for two phase divided by dp by dz for single phase, and this also only the frictional component. This is only the frictional component. Okay, so if one has to do the experiment, they have to actually judicially plan the experiment. So it means judicial planning of experiments include that your experiment should only give you the value of frictional pressure drop. Okay, so what people have done, people have actually taken the constant sized pipeline, and in that constant sized pipeline they have considered purely adiabatic conditions. Purely adiabatic conditions means they try to maintain the same value of volume fraction so that there is not much acceleration of the fluid within the tube section in which experiments are performed. Okay, and third thing is pipes were purely horizontal, so gravitational component was not involved. Under these conditions, thousands of experiments are done for using different conditions, and then people have actually come up with some empirical plots, some empirical equations and some empirical plots based on which one can actually simply use the value of phi f, phi g parameters and then calculate the value of pressure drop for the practical conditions. Okay, so Here one correlation you can see, this is called as Martinelli's correlation for void fraction. So this is Martinelli parameter x and this is liquid fraction 1 minus alpha. So this is measured from different experiments. So all these scatter points are nothing but experimental data, and this experimental data can be fitted by using this single line, and the equation of this line can be written as 1 plus x power 0.8 raised to power entire power minus 0.378. Okay, so the meaning of this is that if you somehow know the value of x, which is your Martinelli parameter, then by simply using this chart you can calculate the corresponding value of liquid fraction in the gas fraction. Is this point clear? So this is one very important chart, or in other sense this correlation is also important, because if chart is not given, then with the help of this correlation actually you can calculate the value if Martinelli parameter is given. Okay. Then whenever we will be doing the application of this, so majorly we will try to see application for flow boiling in straight pipes. So of course from the previous analysis, as I told you, that dx by dz will be becoming 4 phi by dhfg, where phi is nothing but my heat flux. Okay, so that is coming from the previous lecture. And if we have to calculate pressure drop, then I have to integrate this equation from 0 to L, considering that quality is 0 at z is equal to 0 and quality is x at z equal to L. And using this, we are getting this particular equation for pressure drop. So what was the previous equation? That previous equation I have integrated and I have got the value of delta P. Now you can see in the previous equation I was having one multiplier phi FO involved in the frictional term. Okay. So of course when I will be doing the integration, so I will be getting this multiplier as 1 by x 0 to x phi FO square into dx. So this entire term is something which is called as phi bar FO. So this is average Locard-Martinelli two-phase multiplier. Okay. So this is the value. So once if I know the value of this phi bar FO, average phi bar FO, and if I know the value of CFO, means coefficient of friction for a fluid only system, single phase system, then I can simply solve this equation and then I can calculate the value of friction factor, pressure drop. Okay, and in this also one more simplification is done. This entire term over here, in this entire term 1 by rho f is taken common and this entire term is written as gamma 2, another multiplier. Okay, because this is nothing but combination of the properties only and x and alpha. So by knowing the values of property for a particular fluid medium, this entire parameter actually I can either tabulate or I can present this entire parameter in the form of some plot for different values of x and alpha, and then my calculation will become even more simplified. Okay, I need not to substitute values over here, rather I need to simply refer to my table for different values of x and I will be able to calculate the value of this gamma 2 multiplier. Is this one clear? So this is the main equation, and then using this main equation actually we can calculate the value of pressure drop. So these are the different curves. So you can see this is void fraction versus quality of steam, and this is given by Martinelli and Nelson. So here you can see the quality is given along x-axis and void fraction is given along y-axis, and this is for different values of pressure. So 14.7 psi absolute, 60 to 100. So these are different values of pressure. So it means that it is given to you that you have some pipe and this pipe is say maintained at pressure of 800 psi. Okay, and in this pipe the starting quality is 0 and exit quality is say 65%. Okay, you need to determine what is the void fraction within this pipe. So how you can calculate the void fraction? You can refer to quality of 65%, you can refer to this 200, and corresponding to that you will be getting value of say alpha equal to 0.94 or 95, whatever you want. Okay, so this is how you can use this plot. And remember this, whenever they are talking about here quality, they are mainly referring to the exit quality. Okay, considering that at the inlet of the tube your quality is 0, and at arbitrary any length your at the point where you are calculating there your quality value is x. Is this one clear? How to use this plot? All are clear with this idea? Then this is also, remember that this curve is only for steam water mixture. So it means that if your steam and water are present, then only you can use this system. If say you have some boiling tube in which some refrigerant is flowing, then you have to find another plot. Is this one clear? And of course the generalized nature of the refrigerant will remain the same, but the specific values of the pressure will be actually changing. Is this one clear? Then this is two-phase multiplier for, again this curve is applicable only for water. Okay, so here if you know the value of pressure and if you know the value of exit quality, then you can calculate the corresponding value of phi bar FO square. Phi bar FO square means I am calculating average value, whatever this entire term is there. So this entire term I am able to calculate. Okay, I am able to calculate this entire value using this plot. And on the right hand side what I have done, so this pressure was nothing but in psi. So on the right hand side I have given a plot, same plot is there, but now abscissa pressure scale is actually in bar. Okay. Then this is, I told you, another multiplier gamma 2. So this is the curve for multiplier gamma 2 as function of pressure and exit quality. Okay. And then this is one detailed curve for two-phase multiplier, and in this detailed curve you can see this is your quality, but mass flux is fixed. Mass flux is fixed, and these are the different fluids: sodium, potassium, freon. So for their different range of temperature you can actually calculate the corresponding value of the multiplier. So this is a bit generalized curve. Okay, so if you have other than water, some other fluids are given, then you have to use this curve. Now this was approach number 1, in which what you have done, you have actually used the combined phase equations only, but in place of using the same velocity approach, you are using different velocities for each component. So you are doing analysis like your homogeneous flow situation only, but you have just relaxed the velocity condition. And in approach 2, this is approach 2. So approach 2 again I will not take up in detail, because as I told you, approach 2 we will take in more details while we will be talking about the numerical methods for solution of multi-phase flow problems. Okay, but one brief idea I have given you over here, that in case of approach 2 I will be writing the separate continuity equations for phase 1 and phase 2, separate momentum equations for phase 1 and phase 2. So here you can see in continuity equation, when I am writing, then I am writing corresponding fraction of that particular phase, and then S12 is mass transfer between phases. This is between phases. 1, 2 means because of 1 to 2, 2 to 1, and S1 is external source term. Okay, similarly, so this is internal term. So for internal term, if one is positive, other will be negative. So that's why it is written minus S1. Okay, and this is the external source term. Then when we are talking about the momentum equation, B1 is body force, this is pressure force. Now F1 and F2 is kept a very generic term. So F1 and F2 can have now multiple things together. So F1 and F2 will be having the surface forces because of the wall shear stress. Okay, and we know from our very initial lectures that whenever we will be including the wall shear stress, we will be only considering the continuous phase. We will not be considering the dispersed phase in the wall shear stress. So if you have flow situations like dispersed flow, bubbly flow, mist flow, there out of F1 and F2 only one will be containing your viscous term, other will not be having viscous term at the wall. But if you have flow situations like stratified flow, there what will be happening? In case of stratified flow, there will be half portion of the tube cross section is actually covered by fluid 1, some remaining portion is actually covered by fluid 2. So for some portion of the area, there will be viscous force because of the phase 1. For remaining portion of the area, there will be viscous force because of the phase 2. So then if you have some stratified flow like situation, then F1 and F2 will involve actually viscous force because of both components. So that is something which is given over here. So mu1 into del square V1 into del square V2. But other than this also, you will be having some interaction forces between the two fluids. So that also you have to actually account for. Okay. So again, if you simply write that F1 and F2 are the interaction forces per unit volume, then depending upon the volume fraction, you can split these into F1 into 1 minus alpha and F2 into alpha. Okay. Okay, we will discuss this in detail when we are actually talking about the numerical method. So just I am explaining you the second approach for separated flow model is like solve the separate equation. So if you do this, if you have adiabatic flow situation, if you have say heat transfer also involved, then you will be having three equations for phase 1, three equations for phase 2. Okay, so it means you will be having the 6 equations, and then in order to specify the properties, you have to also use some equations of state. So including equations of state, you will be having actually 7 equations. So detailed separated flow models for two fluids will be actually involving the 7 equations. However, whenever we do the simplification, then we try to relax some of the conditions, and then these equations are actually relaxed to subsequent less number of equations. Okay. So approach 2, as I told you, today we are not going to discuss, but just a brief idea I have actually given. Okay, but this is the more generic approach for dealing with the actual separated flow conditions. Okay, the previous approach is still kind of a semi-empirical approach, because only we are differentiating the velocities and majorly we are solving the combined phase equations. Okay, let's try to see one numerical problem using the separated flow approach. So we have a vertical tube of 3 meter length and 10 mm diameter, and this is carrying water vapor mixture. The inlet quality of the water vapor mixture is 0.05. So it means when, if I have vertical tube, so when this is my inlet and say this is my outlet and this is 3 meters, so when fluid is entering, its quality is 0.05. Okay, and total mass flow rate is, so total mass flow rate means W is 0.01 kg per second. the two-phase mixture pressure is, so pressure of this tube is 46.941 bar. Then initial 2 meter of the tube is heated by a wrapped electrical coil which supplies 10 kilowatt of heat to the tube. So say this is my 2 meter portion. So in this portion we are actually adding heat, and rest 1 meter is adiabatic. So there is no heat addition. Okay, we have to calculate the pressure drop using Martinelli-Nelson correlation. Okay, so that is the question. Now, question is clear to all? Let's go to the solution. So very first thing we have to do is we have to actually determine the properties. So we have a air water system. I'll be going to the steam table, and of course when I am operating in the boiling regime, then I will be having actually liquid to vapor conversion. Okay, so I am operating in the liquid vapor dome. So if I am operating in the liquid vapor dome, I have to use the saturation state table. Okay, so corresponding to that, pressure is 46 bar, saturation temperature is 260 degrees Celsius, and corresponding values of dynamic viscosities of liquid and gas, specific volume of liquid and gas, and I symbol over here is for enthalpy. Corresponding values of enthalpies of liquid and gas are actually given. Okay, now by using again the energy balance equation, this we have done in the previous class also. Using the energy balance equation, I can calculate quality at 2 meters length. So quality at 2 meters length will be equal to heat transfer Q divided by W into IFG plus quality at the inlet. So this comes out to be 0.65. All are clear with this? So this Q over here is nothing but 10 kilowatt, and W is how much? 0.01 kg per second. IFG will be IG minus IF, and initial quality is given as 0.05. So if you solve this, you will be getting your exit quality as 0.652. Okay, then if I have to use the pressure drop relations, what I have given you over here, this pressure drop relation. If I have to use this pressure drop relation, then I have to always consider that inlet quality is 0, because in this we have integrated this, and limits of integration were from 0 to x. So the meaning is every time I was considering that my inlet quality is 0. Okay, but now in the question it is given that my inlet quality is 0.05. So what I need to do in order to make inlet quality equal to 0, I need to extrapolate this length. Okay, and I need to extrapolate this length up to the point where my inlet quality is becoming 0. And from this point 0 to point up to 2 meters, first I need to calculate the pressure, then I need to calculate the pressure from x equal to 0 to x equal to 0.05, this extended portion, and then from this total I will be deducting this one, and then I will be getting actually actual pressure for my given pipeline. Is this point clear? Okay, because my formula is derived based on the initial quality of 0, so I cannot start from arbitrary any value of quality. Okay, is this one clear? So that's why we have assumed that we have linear quality increase. So if we have linear quality increase, I have extended this portion back, and I assumed say L dash is the portion where quality is changing from x equal to 0 to x equal to 0.05. Then 2 meter portion is from 0.05 to 0.625, and then remaining portion is having actually constant quality. So if I take the linear assumption will give me that whatever the length ratio I am having, L dash by, say this portion is L1, 2 meter portion is L1 plus L dash, that should be equal to actually the change in quality. So in L dash portion, my change in quality is x inlet minus 0. In L1 plus L dash portion, change in quality is x minus, so x at 2 meters minus 0. So this will give me, I know x inlet, I know x at 2 meter, this will give me the value of extrapolated length, which is 0.166 meters. All are clear with this idea? Once I have done this, then I can calculate my mass flux G. Okay, so G will be equal to W by pi d square by 4. Corresponding to this, I am getting mass flux as 127.4 kg per meter square second. Then what I have done, I have calculated Reynolds number by considering only liquid. So I am using here liquid viscosity. So using this, my Reynolds number is in the turbulent regime. Is this point clear? My Reynolds number is in the turbulent regime. Then for turbulent regime, my friction factor will come from Blasius relation. So this friction factor is coming out to be 0.0075. Okay. So for estimating frictional pressure drop, I have calculated. So basically this FFO is nothing but CFO. So in my formula, it is written as CF. All are clear with this point? Then what I need to do? I need to calculate my multiplier, because in this formula of friction factor, I am having this multiplier also as phi bar FO square. So I need to calculate this multiplier. So for calculating the multiplier, what I need to do? What is my exit quality? Exit quality is 0.652 and pressure of the tube is 46. Inlet pressure of the tube is 46.941 bar. I will go to this curve. 46.941 and quality of 0.62. This will give me point somewhere here. Is it clear? 46 and 0.652. Yes. So somewhere here I am getting my point. So this is 10. This is 20. So in between 10 and 20 there will be my value. Okay. So corresponding to this, if you see, your value of the multiplier is actually 16. Okay. So now if you have this, but of course this multiplier is also based on the assumption that my quality is changing from 0 to 0.52. So when I am moving from 0 to 0.652, I have to use the total length. So total length is 2 meter plus L dash 0.166. So by using this L1 plus L dash, I am calculating the frictional pressure drop and it is 1079 Newton per meter square. Then I need to calculate pressure drop now for exit quality of 0.05, because I need to calculate for L dash portion. Okay. So for that portion, if I calculate multiplier, that comes out to be 2.9 and corresponding value of pressure for x equal to 0 to x equal to 0.05 will include length only L dash. So here value is 14.99. Okay. Then the actual value of pressure for 0.05 to 0.652 will be 0 to 652 minus 0 to 0.05 and this is comes out to be 1064.
सर प्रेशर उसमें इनलेट वाला दे रहे हैं.
Yes.
लेकिन इसमें प्रेशर आउटलेट वाला हो रहा है.
Yes. So this is not outlet. This is delta P pressure.
मतलब जो नीचे वाली एक्स्ट्रा बड़ी है लेंथ, उसके लिए तो आउटलेट ही हो गया 0.05 का मतलब.
Yes. Yes. Yes.
तो इससे क्या ठीक है मतलब.
Yes, because whenever these plots are derived, these are for the corresponding inlet pressure condition of that particular tube. Okay, so here what we are saying that this portion from say this was your actual length and this portion is minus of 0.166. Okay, so this portion from actual inlet to 0.166 behind the inlet, this 0.166 is a very small distance. So in this very small distance, your pressure condition will be almost same. So of course there will be certain error, but that error is actually very small considering the length of the pipe is actually small. Is this one clear? Otherwise, if you have to go for very accurate thing, then what you need to do, first using this assumption of pressure, you need to calculate this pressure drop, okay, this 14.99. Now from your 46 bar, you need to do minus of 14.99. But 46 bar, if you do 46 into 10 to power 5, so this difference is actually very, very small. Okay, is this point clear? But if say in some cases this difference is significant, then every time you need to first do this subtraction and then keep on doing this iteratively till the time your consecutive two steps are actually not. Okay, but here considering that length is small and value of pressure is very, very small, so that's why we can actually assume that. Okay, so this is all about the first component of the pressure. Now second component of the pressure is, so till now I have calculated this term. Now second component of the pressure is G square, and this entire term I have written as gamma 2. Okay, so I need to do now simply G square into gamma 2. And gamma 2 also I can calculate from this particular plot. So I know the value of pressure, I know the value of exit quality. So if I know pressure and exit quality, I can calculate the value of gamma 2. Is this point clear? So that is what I have done over here. For quality of 0.652 and pressure of this, my value of gamma 2 is 15. For quality of 0.05 and pressure of 46 point, this my value of gamma 2 is 1.2. And now what I need to do, acceleration pressure drop will be equal to acceleration pressure drop from 0 to 0.652 minus 0 to 0.05. So which is G square times Vf into gamma 2 for x equal to 0.652 minus gamma 2 for x equal to 0.05, and this is coming out to be 286 Newton per meter square. Is this one clear? Then again what I need to do now, I need to calculate further third component. What is third component? This is third component. G cos theta 0 to L 1 minus alpha rho f alpha rho g into dz. So it means, of course, this 0 to L integration will give me x over here. Okay. So what is alpha? Alpha is nothing but void fraction. So I need to determine the void fraction also. So how I can determine void fraction? This is the plot. If I know exit quality, if I know pressure, I can calculate corresponding value of void fraction from this plot. Okay. So for exit quality of 0.652 and pressure of 46, my void fraction is 0.93. For exit quality of 0.05 and pressure of 46, void fraction is 0.55. Now this, after integration, you will be getting that z you have to replace in terms of x. Okay, and then you will be getting your final formula as Lg sin theta divided by final quality into 1 minus alpha rho f into x, alpha rho g into x, and this integration is from 0 to 0.652. Okay, so now you know the value of alpha as 0.593 for first case, which will give you the value of 1509.4, and for second case value of alpha is 0.55 and you will get value of pressure as 595. Then value of pressure from 0.05 to 652 will be this minus this, which comes out to be 913.9 Newton per meter square. Okay.
इसलिए यहाँ पर sin theta उसमें शायद cos theta
Sorry.
ये जो sin theta इसमें इसको वहाँ शायद cos
Okay, so the difference is when you are deciding the axis, you have to consider whether you are referring with reference to vertical or with reference to horizontal. Okay, so as you are having a vertical tube, so of course sine and cos we have to choose in such a way so that sine theta or cos theta is becoming equal to 1. Fine. So this depend upon the reference. Whenever I will be giving you the question, I will actually specify the reference. In the previous formula, reference is with reference to, yes, okay. So then my total pressure drop will be frictional pressure drop plus acceleration pressure drop plus potential pressure drop. So that is nothing but my total pressure drop. But this total pressure drop is now only for which section? Heated section. When you have unheated section, then further you need to solve for that. But one benefit in the unheated section is that in unheated section your quality and void fraction will remain same because there is no heat transfer. Okay. So what you can do that, this is your total pressure drop for heated section. For unheated section, again this is the slide. So these are the multiplier values and this is alpha highest 0.93. Corresponding to this you can calculate all the components, frictional as well as acceleration as well as gravitational, and then if you do the sum of these, this will be your total pressure drop for adiabatic section, and if you take sum of heated section plus adiabatic section, then this will be your total pressure drop of the pipeline. Okay, so I will be uploading this slide, so all of you please go through the adiabatic section, and if you are finding difficulty, then we can discuss it further. Okay, because this is easy now. Adiabatic section I have actually described you in the previous discussion as well. Okay, all are clear with this idea? So with this we will be completing our discussion on the separated flow model. We will not go into much more deeper details, but of course please do this numerical problem, practice this, because this is the most generic problem I have given you over here. Now using this by simplifying this problem, many other simpler problems actually can be designed. Okay, all are clear with this?